Welcome everybody. Today we're going to take a look at these guys here, which should hopefully kind of shed a little bit of light on capillary action. So before we get into that, I kind of had this stuff out here sitting in the kitchen and thought I'd review a little bit of what we'd talked about before. By now, you should be kind of familiar with when we saw this guy and these guys, and kind of a little demo where we had basically just sort of a way to simulate solids, liquids, gases. So if you look at these guys, all those are supposed to represent little particles. As I introduce this little bit of motion here, you see they kind of flow past each other. If I were to cram some more of these little clay slingshot ammo pellets, little clay balls here, into there, what you'd find is it locks up and it'd become more like a solid. So this is supposed to represent our liquid, and here, nothing too fancy. I just got a basic little dropper with some water in it, and I've had this pan on for a bit. And so some people will say that water's disappearing, and to some extent they're correct, but I want you to understand that it's not just disappearing. In fact, matter, or anything that has mass and volume, can't just disappear. Matter can't be created or destroyed. So essentially what we're seeing is these liquids, or that liquid, that water, becoming a gas. So when the liquid becomes a gas, what we see happens is things move so fast, and you add that extra bit of energy, that it behaves a little bit differently. So notice here that even with just a few of these guys taken out, I'm trying to give this the same amount of shake, but what you see is that these particles, they're moving faster and farther apart until they eventually collide into the wall of the container. So this isn't an exact replica of what takes place, and there's definitely some things that we're stretching a bit, but hopefully that gives you a little bit of a visualization. So what I did want to talk to you about today was capillary action, which is a pretty unique property of liquids. So if you take a peek at this, I've got two glasses. One is empty, and the other has some blue food coloring. There's actually a little pellet that came from some leftover Easter egg dye that we had. And here, I've got a regular old paper towel that I just folded up. And if I take this, and I were to fold it in half like that and put half into the blue side and half into the empty side, what's happening right now really shouldn't be like a huge surprise, right? I mean, this paper towel is absorbing, but I want you to kind of think about the fact that that's going against the flow of gravity, or the pull of gravity. So what's happening there with that capillary action, it's actually kind of a pretty neat process, and it's unique to liquids. So capillary action, it basically occurs because water has a cohesive and an adhesive characteristic. I'm simplifying this an awful lot, but as we can kind of see, this is sort of slowly making its way up against the pull of gravity. The water wants to have that cohesive adhesive, and like I said, there's actually an awful lot more going on there with the polarity and the charges of the water, and it's pretty complex. So I don't want to get too far into it with just our first little demo here. What I want you to kind of think is water has a cohesive factor, which basically means that it's going to stick together. That prefix co, it means together. So cohesive means it sticks together. And it's also got an adhesive characteristic to it, which means that it's going to stick to some other stuff. So you've probably figured by now, I'm not much of an artist. But when we start to get into density, we're going to need graduated cylinders, which we can use to measure volume. So this is supposed to be like a little tube. And if we were to fill it with water and then drop something in there, the amount that the water gets displaced, fancy way of saying moves, we can measure how much volume or space that object must have taken. But I don't want to get too far into that today. What I do want to say is, what you'll notice when we use these graduated cylinders, if you look close, the line will have a little curve to it. And there's a fancy name for that. It's called the meniscus line. And you get water that kind of sticks or adheres from the adhesive and kind of pulls itself up from the cohesive. So this meniscus line is also a pretty unique factor that happens with water. So the more we study water, the more we'll see it's just a really unique substance. There's an awful lot of neat stuff going on there with its surface tension and its viscosity and its ability to dissolve and what happens to it when it changes phases. But right now we're just kind of looking at the capillary action. So this has slowly made its way up even further. And that's because of capillary action, that cohesive and adhesive factor of water, and the fact that it can kind of stick to things and pull itself up. Again, there's a lot more going on, but if you can just kind of picture that happening in your mind, the water pulling itself up, I think that would be okay. So some things like here, I just cut up some of my kids' paper. It's just like kind of confetti, right? If I were to do one of those, this does not stick together, right? I mean, there's nothing there that's keeping all of this clump together. Whereas if I look at a water bottle and took a sip out of this guy, you can see that the water, remember the way we're describing a liquid, it's got set volume and not set shape. So the amount of water, the space that this water takes up, it's gonna stay the same. But if I were to go back to the frying pan here and pour this water out, it's cooled off a bit. Now it's taken that shape. But the amount of space, or the space that water takes up, it would end up being the same. But notice here though, a little warm to the touch. The water wants to stick together. Whereas if I've got little paper here, it does not. So I would say that this does not have that cohesive or adhesive characteristic. And believe it or not, water's kind of sticky, which seems kind of weird, right? Like if there's jelly on my countertop here, I might use water to clean up that something that's sticky, but water tends to stick to things pretty well. So I'm not gonna bore you with just staring at this for hours on end, but what I do want you to know is that if this is left alone, over the course of a few hours, what you'll find is this. So this worked out to perfectly reach equilibrium. That's a fancy way of saying equal. And that was my dog, by the way, if you wondered if that was like a scalded monkey. Anyways, this reached equilibrium. So this water actually made its way up the paper towel and back down into this cup until it perfectly balanced itself out. So I'm thinking the next time my two kids are squawking about who gets the more chocolate milk in a cup, I might just have to pour out 2 glasses, put a piece of paper towel over, chocolate milk into one, and let it perfectly work itself to equilibrium. That way I know for sure that they're gonna have equal amounts of chocolate milk. So hopefully that kind of sheds a little bit of light on capillary action, and you've learned a thing or two. A little bit of review is peppered in here as well. As always, if you got any questions or concerns about anything discussed, please feel free to see me. Until we meet again, bye-bye.